I'm Paul Middy and I chair the CREST board. I wish I could say this is our nth CRESTCon, but to be honest, I've forgotten how many we've done. I'd like to thank our sponsors. I'm not going to read all the names, there's quite a few, and I will probably forget them. And I think you've got cards this year that you can get stamped to win prizes, so please do remember to do that. I'll be introducing the speakers this morning. So first up, we've got Alex Farrant, who's a senior consultant at Context Information Security, and he's going to be, I would certainly hope, explaining to us how to spy on people using IP cameras. So Alex, please.
Morning all. I'm Alex Farrant, senior researcher from Context, from our Cheltenham research team. And I'll give you an explanation about why I'm telling a room full of security experts about IP cameras. Because 10 years ago, there was headline news that IP cameras were bad, that weirdos could look at IP cameras on the internet. Well, full disclosure, I was one of those weirdos looking at people's IP cameras. And that even though we've moved on 10 years forward, a lot has changed, a lot hasn't changed, and now things are cloudy, and everything has an app. And as I'll show you, these new layers of abstraction have actually made these things even more compromisable than they were before. If you thought they were bad 10 years ago, they're even worse. The camera we picked, and we did literally just go on Amazon page one, throw a dart, was quite a popular product. It was an outdoor security camera, the Motorola Focus 73, part of the Motorola Focus family of IP cameras. And it's got a big attack surface, as you might imagine, from a modern IoT gadget. It's got lots of interfaces, wireless, wired. It's got an app. Everything has an app these days. The app is ridiculously easy to set up, and it has a cloud infrastructure wrapped around it with a new business model wrapped around it, which I'll explain more about later. And that's provided by Hubble Connected. Hubble Connected provide this ecosystem for IoT devices. Your video gets uploaded to the cloud and gets held to ransom. You have to pay extra to view that, be a premium customer. And you can view it from anywhere in the world. So that's the advantage of this over legacy IP cameras. You can now open up your app and view your camera in New Zealand, or view all your cameras in New Zealand. It traverses NAT routers with stun. In the bad old days of products on a LAN with a NAT router, you needed to set up port forwarding and go and forward some ports so that you could access your devices behind your firewall. This mitigates that. It does it automatically using stun, and it's just magic. You plug it in and it works. It connects to the internet and you're able to access it. And as we'll show you, we use that same principle to exploit these devices. The teardown then, so when we get a product, we get it on the bench, we open it up to have a look at it, to see what's inside it. And it wasn't particularly impressive. You can see the soldering at the top there is not very premium. It actually fell apart when we opened it. The first surprise, and it was full of surprises, was it wasn't made by Motorola. It was actually a rebranded product with a Motorola name on it, made by Binatone. And if you ever see MBP, that's a Motorola Binatone product, that's what they use to describe their product line. The board inside, the PCB, was a Nuvoton board, which is very standard across not just Motorola Focus cameras, but also Blink cameras and others. And so there's a lot of standardization here. It's running a Linux kernel on an ARM processor, and the software that's layered on top of that is made by a small Hong Kong firm called C-Vision. Most interestingly, there was a pair button on the back of a camera, a small micro switch, which is how you pair it with your app. And the idea is that you press this button and it appears on your phone as if by magic, and then you're synchronized. And the magic, unfortunately, was just an open AP, and your phone is a client to that AP. And if you want to mess with it later, it's actually on the table out there. You can go ahead and press the button and see what I mean. It's got a load of services running on there. It's got BusyBox, MJPEG streamer, and it's actually an upside-down baby monitor. It's a product that they've actually just flipped 180, and you can confirm that in the firmware. The app then, so it's quite a slick-looking app you can get for free from iOS and Play Store. and it allows full control of the cameras. And concerningly, when you do the pairing process, that button I talked about, it will ask you to pick your wireless network, enter your PSK, and it will then broadcast that PSK in clear over an open AP to the device. If you're going to do this, I recommend you do it early in the morning, whenever all the bad people are asleep, or do it in a Faraday cage. It's not very good. And the firmware update, there's a firmware update functionality within the app, and that's also just posts an unencrypted file that's not signed or checked to an obscure URL on the camera. And as I'll show you in a minute, that's easily exploitable. To explain the architecture then, you have the phone which never talks directly to the camera. So this is the difference between new IP cameras and old IP cameras. You talk up to some cloud servers up in the Amazon cloud in this case, and they communicate via a hidden protocol to your camera behind your NAT router, which is quite interesting. You can do all the usual stuff over here, so you can control the camera, get the video feed, send ad hoc commands with an inherent delay, and in return, your camera can broadcast video direct back to you. So first thing we wanted to do, so we've got this thing on the bench, we want to break it, get root on it straight away. A quick way to do that, once we looked at the traffic between the app and the camera, and we saw the firmware update URL, we thought, right, let's go and grab that firmware, have a play with it. We got the firmware, was disappointed to find it was just a tarball. We opened it up, added a web shell, uploaded it, and had a root shell. It was using a scripting language called Hazel. Hazel is a very simple and very dangerous scripting language, which the author rightly says this is dangerous, use at your own risk, because it will take any arguments in a CGI script and put them straight into the shell environment as root without validation. So that red writing there is all you need for a web shell, just Hazel command, and you can then execute as root. So the command I executed here was just to cat out a config file, and this was quite an interesting config file, which one of the media outlets made a big play on when this hit the news last month. It was a testing configuration file which should have been removed in the QA process before this product was shipped, and it contains Gmail credentials with password, Dropbox credentials, FTP credentials, and this is all for the developers of the product. It doesn't need to be on there. We did check to confirm that this wasn't in play, this wasn't live, nobody was getting duplicate copies of your movement alerts, and it was just for testing. But we weren't able to validate whether those credentials were genuine under the Computer Misuse Act, but I think you can imagine they probably are. Hence why I've blacked them out. So what else did we find? Wireless password. So earlier, your wireless password was sent in clear over the network. Well, it was just sitting in temp in clear. Those of you who are familiar with WPA supplicant know that you can use WPA passphrase to obscure the passphrase, but these guys didn't, so you could just bag it from there. Those developers' creds, the root password was not particularly good, and the logs also contained an encryption key for remote control of the camera, and you could download those logs from the web interface. The logs were encrypted, however, they were encrypted with a hard-coded key, which, funnily enough, contains the name of the company that wrote the software. Alerts, the camera does movement alerts, and that's a bonus feature of this for a security camera, is it will detect movement and it will fire off a JPEG and a 5-second FLV video clip. If you can overwrite the DNS file, you receive those movement alerts, and we did that, and that's a real bonus if you're looking to compromise cameras within an organization and receive a real-time feed of movement within that organization. It's a pretty powerful surveillance tool, I think you'll agree. Interesting, looking in Cron there, the camera, and this is a 24-hour security camera, reboots on a fixed interval. It's a very precise interval because it uses NTP to sync the timestamp. So that's probably not a good feature. Now, you might wonder, why does it do that? Well, the reason is it has a huge binary running on there, not a lot of process resources, and that binary is leaking memory. And so they reboot the camera because it's leaking memory. I talked about the premium customers and the different grades of usage of the product, well, that can just be enabled via a Boolean in a config file. So as well as security risks, there's a real business risk here because somebody can make open source firmware for this and effectively make everybody premium overnight. And there's lots of tools on there. If you're a bad guy, there's all the tools you'll need to do reconnaissance and also pivot to more stations within a network. You've got BusyBox with Netcat on there already. Poking around then, so we started, so we already had root on it, but then we still wanted to hit it from other angles, and we ended up coming up with three ways to compromise this device in total. Looking at the web server then, a properly configured web server should not barf out the contents of its scripts, especially CGI scripts. So this product actually had two web servers. It had one running on port 80, which would not port 8080, which would not reveal the contents of the CGI scripts. However, if you visit the same page on port 80, it barfs out the contents of the CGI script. And that was fascinating, because not only would it barf out CGI scripts, it also barfed up ELF binaries. If you knew where they were, you could dump any file, because it wasn't a proper web server. It was an MJPEG streamer server. So we looked at this script here, so we thought, right, that's a badly configured web server then. We then had some scripts. We had a look at them. This script was particularly interesting. I'll zoom in later onto line 7. Line 7 is taking input from a user, performing no validation, and then putting it into the shell environment as root. So you control that, and it's in a move command, which is great. So this is a file upload script. So not only do you control the file that is being uploaded, you control the name of the file as root, anywhere you like, no input validation. So we've got directory traversal. We could brick the camera. We could overwrite a core binary, which for a security camera is pretty bad, because you could effectively brick it instantly, make everybody go black. And it's pretty poor script. So we set about running our own Hazel script to see if we could exploit this. And sure enough, we could very easily, first chance, get directory traversal. So we could put any file we liked anywhere we liked on the camera. We were testing this with our own script, and it was working, but something later in the process was stopping it. There was quite a convoluted process from a CGI script to a binary to a shell script. And this was all part of the update process. And somewhere in there was a tidy up process at the end there. It was tidying up and removing the firmware, because you don't have a lot of storage on a little device. And these firmware files are quite large. So we wanted to break that process, and we needed to look for a weak link in the chain to break it, to cause the process to fall down, and for our bad file to persist. And so we had a look at this binary, because we decided that is probably the best chance we've got of breaking it, to see what the binary does. And this binary was quite crazy. I can't think of a more concise way to describe it. The CGI script would write the file name to a text file. The binary would then read the file name from the text file and then continue the process. So it's trusting that the name that's in that file is good. It's also making a bad assumption that the file name is within this size. And so all we had to do to break it was just make the file name this size, make it even bigger, and then it wasn't able to read the full file name, and the process was broken, and we could then persist. So it's expecting 128, you just have to give it 129, and you've broken it. So this was our directory traversal exploit. We created a file name which was really long. It doesn't matter what you use to pad out those 129 bytes, but we just used a file path there. So we went forward into the web root, backwards into the root file system, and back and forth until we exceeded 128. And then finally, we finished with the destination for the cron folder. Anything within the cron folder, any cron job there is executed every minute without question. And you don't have to reboot the cron service, which is really nice. So we just created a cron job. This is a cron job for a reverse shell using netcat every minute. So a shell delivered to your door every minute for life. And lo and behold, it's uploaded that, and we got a reverse shell, which was really nice. Amusingly, after we had executed this, we were taken to a progress page to show you the firmware update progress. And sadly, it never made progress because the process had died. It stayed at 0%. It showed you this very long file name and that it was only 57 bytes. That wasn't suspicious because it just isn't checking. And 60 seconds later, we had a reverse shell. That's nice. We can do that locally. But we want to scale that up. We want to do it remotely. We want to do it to lots of cameras at once. We want to send somebody a link and compromise all the cameras in an organization at the same time. That would be really cool. So we used some JavaScript, wrote a bit of JavaScript. There's two JavaScript exploits there. One does the reverse shell, which I just described. The other subverts the DNS. You could probably argue that subverting the DNS is even more powerful because you then instantly get a real-time movement feed coming back to you rather than just a load of shells, which you're going to have to administer and tidy up. We use JavaScript reconnaissance to scan a LAN. So we've got some JavaScript that we used in a previous piece of work we did for the Canon printer, whereby we compromised a Canon printer that was behind a NAT router. And that just tests for images on local devices. And if it finds an image that it regards as a signature of that being a device, in this case a Motorola IP camera, it then fires off a bit of JavaScript to exploit that device. This is a demo of how that works. So we're basically talking about cross-site request forgery here. An attacker has prepared a web page with his bad JavaScript, innocent victim bridging the boundary of the company's LAN and the bad internet, visits the web page. Their web browser then scans their LAN and compromises all their devices, printers, cameras in this case, and the attacker gets his root shell or his movement alerts, whatever he's after. Just a demo of it in action there. So obviously the victim would not see the HTML that's there. They wouldn't see that. But if they looked in their network log, what they would see in their browser is lots of repeat calls across a local IP range looking for images. And these images are signatures that are fairly unique to that device. And when it finds one, yes, it found one on 1.5, it then fires off a post request to the vulnerable CGI script to exploit that device. And what do you get in return? Well, if you stand up a web server and you stand up a DNS server, you then receive this Orwellian feed of JPEGs and video files helpfully tagged with the MAC address, that's the Wi-Fi MAC address of the camera, and a timestamp accurate by NTP. So very rich intelligence feed there. In order to process these, you just need to write a little server-side script to receive, in any language, to receive those files as they're posted. They're just unencrypted HTTP posts, and then just park them in the folder. Or maybe make your own folder structure, depending on how many cameras you aspire to compromise. Right, apologize for this slide. It's a little bit dry. However, if you're into crypto, you'll probably lean forward at this point. This is about a poor crypto implementation we found on the camera. So we were curious as to how the camera was controlled, because clearly you've got an app, you can press buttons on the app, and the camera gimbal moves and does things. And so we were watching it with Wireshark, and no matter how many times we tested it, we couldn't see it. We couldn't see the packets going to the camera. And but what we could see is lots and lots of stun packets going backwards and forwards. Now, stun, session traversal for NAT, is meant to be used in support of other protocols, the same way DNS is used to support HTTP, for example. You're not meant to use stun as a communications protocol. It's just to enable you to resolve what your WAN IP import is and to do a bit of hole punching. So they were misusing stun to smuggle encrypted commands to the camera. And why not? Because it bypasses NAT. It's traversing NAT by design. And so we were looking, it was staring us right in the face. It was the stun packets. And they were using the stun as the way it should be, at the top of the stun packet, but then at the bottom of the stun packet, there was an encrypted blob. And we had a look at that encrypted blob. We did some reverse engineering on the binaries on the camera and concluded that it was pretty poor crypto. It was AES 128, but they were calling SRAND with Unix time, which is completely deterministic. You can repeat that in the future. So it's not good randomization. That's not clever. And the IV was almost pointless because you're only meant to call an IV once but they were calling it each time with each packet. They were calling this srand function, and then the IV was the first bytes in each packet. So it was quite easy to, once we figured it out, to pull it out. So we already had the key. You can steal the key from the logs. I mentioned earlier you can download the logs from the web interface. So we had already stolen the key, but if you haven't stolen the key, you can actually set the key. There's a URL at the bottom there, command equals set master key, and just put in a 16-byte key and the camera's yours. And you can then knock up your own Python script to generate these stun messages and control that camera remotely behind a NAT router. We were mildly impressed at some of the bad security we were seeing. We looked at this encrypted discrete command and control channel, and we thought, actually, that's quite good, even though the crypto implementation needs work. And we had a look at the whole thing and where the two met. And what had happened is the crypto API was from Hubble, and the poor HTTP API was a legacy API from sort of 10 years ago. And where the two meet on the camera, you have this security train crash, which you can see here. Green is encrypted, red is unencrypted, and the camera decrypts these messages when they come in. It then calls curl to call the old API, the unencrypted HTTP API. So it decrypts it, almost comes out of the castle, and then back in the castle through an open door. It's very strange. And so if you know that, you can just, and you're able to touch it via HTTP, you don't even need to worry about the encrypted stuff. I don't know how well you can see that at the back, but this is a blind attack. This is the camera's web logs. And so the scenario here is that we are just blasting a WAN IP with these encrypted UDP packets, looking for a response. You're not going to get a response on the path that you came in on. It's a blind attack. And so we're blasting it with these encrypted packets because we know they've got these IP cameras on the other side. And this blind attack is actually a really useful blind attack because it's starting remote video. And so if you can send the command to start RTMP, well, first of all, you send the command to set server, and then your IP. And then the second packet that you send is start RTMP. That will then immediately initiate live video streaming to you, which is pretty helpful. The confirmation in the logs here is that it's connected to a video server on your domain. And interestingly, from the URL there, you see the name Blink HD. Blink are a completely different brand of cameras, but that gives you an idea as to how sort of widespread this firmware is. This is us doing the stun packets. So Wireshark is showing some stun packets going from the other side of the NAT router there, and you'll see from the packets that they're valid. So we're sending in a packet, and we're getting immediate response saying that packet is good, it's valid. So it's decrypted it, it's unwrapped it, it's executed the command. But if you look down in the body of the packet, you'll see context owns you. And we did find some space in the header of the packet to put in some silly words, just to demonstrate that this is not an official packet from Hubble. The IP might look like Hubble. If you go and resolve that now, that should be Hubble connected, but it's not. That hasn't come from the cloud. It's come from us. We used hping-free to spoof those. They're just UDP packets. This is what a movement alert looks like. You see the door handle, it's just gone down. It's fairly sensitive. The resolution's not the best, but you get what you pay for. It's fairly useful as a surveillance tool because you get these real-time alerts. After Matt came through the door, we then got a video clip of Matt walking down the corridor, which we would have had to have paid extra for, but in this case, we got it for free. Right, summary of issues. I've talked about most of these. There are lots and lots of issues that should have been picked up in the design process, in the QA process, and it's just a raft of issues. We worked, responsible disclosure, we did this back in October. We worked for over 3 months with the company to get this fixed. It wasn't easy because the company is spread out all around the world. So we were dealing with a chap in Canada who was dealing with chaps in Hong Kong. And we needed to give them extra time just to get it sorted. But in the end, it all worked out well. They were pleased that we had helped them. We got some interesting responses in the process, though. Some of the stuff was complicated. Certainly the CSRF side of things is quite complex initially to get your head around. And some of the responses we had back, we found quite eye-opening, because this guy was a CISO who is in charge of security for a cloud ecosystem. And, well, you can read for yourself there. Who's saying, I can't repeat the exploit you show me, but it's not a full stack of Linux, so root isn't all that useful. Well, we found it quite useful. We were able to explore the LAN, explore wireless networks. You've got WPA supplicant. You can do all sorts. And then the second quote there was the scans raise a concern that's limited by the extremely limited functionality of the camera. In the past, we used to say that compromising a printer was probably the best thing to compromise in an office, because it's always on. Nobody ever checks the security of it. If it's working, just leave it. I'd say an IP camera is even better, because it's got the same advantages of a printer, but you've also got video and movement alerts. Any questions? Yes?
You mentioned you spent research. How long did it take you guys to
We had root on the camera via the firmware upgrade in 24 hours. We had root via the other methods within a week. All in all, and the blog and media took longer than the exploiting. All in all, 2 weeks. The disclosure process was about 3.5 months. Okay. Yes.
I was wondering if the Motorola not only fixed the issues with the piece of kit, but looked at the development processes related to their software. So, for instance, if the features of Stun that were used in a way that Stun wasn't initially designed for, who says you can't use that feature? Is that your opinion, or does the community agree that Stun should not be used in that way, or is it just a convention that can be broken because it's going to be convenient and looks like an easy way of getting an encrypted feature into the product?
Very, very good question. I think it took us by surprise is the answer. And in our opinion, it was quite sneaky. We expected something a bit more standard, maybe HTTP, SSH. Wireshark was not able to recognize the encrypted blob as being a command, because it was a reserved area of the Stun specification. So actually, they hadn't gone off piece. They had just been quite innovative.
Yeah. So they actually thought it was a positive thing to do rather than a...
Yeah, and I still believe that if the crypto is sorted out, that is a valid way of communicating and controlling IoT devices. It works well for NAT routers, certainly. Absolutely, it's a very capable device. It is a Linux computer with wired and wireless interfaces. It has, I think, about 50 megabytes of disk space and cloud connectivity for further storage, because the API it posts to in the cloud, from what we gather, and we weren't pen testing the Amazon cloud instance, has no storage restrictions. So if you were to craft a so-called video alert with a agreed file name that was maybe a gigabyte in length, it would probably accept that. So you've got elastic storage. Yes?
Given that at the start you indicated there was a lot of commonality of components, certainly on the hardware side of things, so I presume that you're going to see similar problems with other devices. I mean, is there any sort of guidance if you were to say, well, how would I choose a camera which is going to have better security, or how much of it is actually in the firmware that the individual vendor will develop for the product?
Sure. The underlying kernel in this camera, the Linux kernel, we believe was actually nearly 10 years old. The firmware was layered on top of that as a sort of subset of folders on top of a root file system, and was from a different company. So you had the Nuvoton PCB, and then CVision's sort of folder structure that sits on top of that. We were aware, whilst we were picking this apart, that this code was clearly in use elsewhere. CVision do not just do the Focus 73, so what we didn't want to do was go on a responsible disclosure marathon and contact every possible vendor who might have done business with CVision in the past. There is a real risk that code is elsewhere. You asked about recommendations for choosing a solid IP camera. Yes. After on our blog post, after we had finished throwing rocks at this thing, and we did have a big pile of rocks, we then listed recommended steps for securing the device. And our first recommendation was firmware update, signed and encrypted firmware as a minimum. The firmware update process that allows anybody just to monkey with the firmware and upload their own is not good security, and it's not good for their business if they're relying on locking people into a product. Okay, thank you for your time.
Alex, thank you. We're a bit under time at the moment. Alex, I wanted to ask just one question myself. I was a pen tester some time ago, and a lot of the things you described were sort of relevant probably 10 or 15 years ago, directory traversal and that sort of thing. Do you think with the rise of connected devices such as this, are we going to kind of see a wave of sort of old school attacks again, and companies using old software and that sort of thing? And how widespread do you think this problem is going to be?
I think it's very widespread, and you will see a lot more of this in the next few years, certainly. But I'm well aware that the FTC in the States are wielding some big sticks against vendors who are producing products of this standard, and as a result, you will see the bar raise, and a lot of these gaping holes that we've discussed there patched.
Mm-hmm. And do you think there's going to be a fairly steep learning curve then? Because I get the feeling that companies that are sort of moving into IP-connected devices, the obvious trivia like kettles and toasters and that sort of thing, they're going to have to go through a very similar learning curve, aren't they, as the sort of Microsofts of this
yes,
world?
Yes, and I think Binatone especially are a great example. But Binatone's selling point has been innovation. They've always been very innovative and first to market with new ideas, and that comes at a price, and we've shown that price today. So they certainly have a steep learning curve where IP connectivity is concerned, because this is an example of a legacy infrastructure that was safe almost behind the LAN that is now opened up to the big bad internet, and it's failing the security test.
Yeah, excellent. Well, thank you, Alex. That was a very interesting presentation. We've got about 10 minutes or so before the next one, so if you want to take a comfort break, please do. I can thank our sponsors again. There's probably this isn't working. But do take a comfort break, and please, the next presentation is at 10:20. You can move to the other streams, but I suspect they'll still be in session, so if you could wait until the doors open. Thank you.